the talk. So I would like to introduce Emanuel Guariglia. He's going to be our first speaker in this afternoon session, and he's going to talk about Vieta-Lucas wavelets. The floor is yours.
Thank you. Thank you for a nice introduction. Okay? Okay. And thanks to the organizer, Mateus, Emanuel, or Emanuel as you prefer, and Felipe. In these 25 minutes, we will say something about Vieta-Lucas wavelets. This is a kind of new family of wavelets. I mean, the orthogonal polynomials is not new, but it's few years that these wavelets appear in current literature. And as we will see, they are very similar to Chebyshev wavelets. So the first challenge is to understand in which way they are different, and to see drawbacks and advantages and so on. One nice thing for me was that my first conference was in IMPA 10 years ago. So I had this conference here in number theory and physics, and almost 10 years after, I'm here another time in a conference of harmonic analysis. Okay. So this is the classical definition of a Vieta-Lucas polynomials. Now, in literature, you will find different definitions. In some cases, you will find Vieta-Fibonacci and something like that. We can say that Vieta-Lucas polynomials and Vieta-Fibonacci polynomials are in the same relation as the Chebyshev polynomials of first, second, third, and fourth kind. This is the idea. So these are like the first terms of these polynomials. And as I told you, we can have the Vieta-Fibonacci polynomials of order n, which are given by this expression. Okay? So, as often occurs in orthogonal polynomial, we have a recurrence relation. And this is our relation 1. If you want to have more details about this class of orthogonal polynomials, you can see Horadam. I guess this is the pronunciation. I will show you the paper at the end. So, it's a way to write n of x in this form. So this looks like a power series. And here just, I report this proposition to show that as in cases of many orthogonal polynomials, we have many properties. Here we have the classical binary form, Simpson formula, and so on. So, we don't stay here to discuss all this property because this refers to a class of, special function or similar classes. Okay? But the difference between Vieta-Lucas wavelets and Chebyshev wavelets depend on the inner products. So this is what's happening in the case of Chebyshev polynomial, and if I can, okay, here. So this is our inner products. So our weight function stay here between -1 and 1. In the case of Vieta-Lucas wavelets, we have this. Okay, it's possible to prove this proposition. It's quite easy. Okay, so x go from -2 and 2. So if, and here we have this inner product. So this will reflect on the definition of Vieta-Lucas wavelet. Okay, so more things. Generally, these polynomials can be defined as solution of this second order differential equation. There is also a Rodriguez formula. Okay, I didn't find the proof of Rodriguez formulas on the web. It's easy to prove this. For sure, some author proved it somewhere. I gave a talk on this topic in the mid of May, and one researcher from the University of Coimbra, Portugal, told that this is a particular case of the Bocher theorem that should be 1922. So this is our definition. In this definition here we see the shift here. That is quite normal for these wavelet families. And here we see that with ni tilde, these two terms here depends on the inner product. Okay? So, oh wait. So we have this because of the inner products. Okay? So basically we can say that this is one of, because we have a Kronecker delta. When m is equal to 0, this quantity here is 1 over the square root of pi. Otherwise, we have 1 over the square root of 2 pi ni m. And you can see the difference with the Chebyshev polynomials. Here we can go quite fast. You see, it's very similar here, and also this term here, Tm. Just that these wavelets comes from the Chebyshev polynomials of first kind. Okay. For what I remember, it's also possible to have Chebyshev wavelets starting from the Chebyshev polynomials of second kind. There is one paper that examined the case of first, second, third, and fourth kind. Okay, so this one problem is this. Suppose we have a function and we want to reconstruct our function. If we want to reconstruct the derivative of this function using our wavelet basis. Here we see the case of Chebyshev wavelets, but we can easily do using the Vieta-Lucas wavelets. So you see, we have this situation here. And so, this is what's happened with the first derivative. It's possible to prove this. For the other cases, we have, if we go back here, so we have to examine this, the derivative in the right-hand side. So the idea is to expand the derivative of our wavelets using the same wavelets. When we do this, we are having a problem that involves the so-called connection coefficients. Okay? So now connection coefficients can have a very nice representation or a very bad representation according to the wavelet family we have. In this case, here I report the case of Chebyshev wavelets, and the situation is, let's say, it's a work in progress. And I will explain you why. Because in this case, we have an orthogonal polynomial that is, and the inner product is defined with respect to a weight function. Okay? And this creates a problem when we want to find gamma, our connection coefficient, because we cannot use Parseval. Okay? There is not a version of Parseval in a weight spaces. This is a huge problem. And so the sort of theorem I will show to you was a theorem proved in in a domain. I wasn't able to go in the Fourier domain. This is an open problem now. So for all the class of wavelet bases that are defined in this way, so we talk about Chebyshev wavelets, Vieta-Lucas wavelet, and all these wavelets, we have a problem. And there is, so this also open another problem. Is there an equivalent of the Parseval equality in weighted spaces? This is also, like, to me, for me, it's, so if we fix this and we write Tm in this way as this is like just a sum of polynomials. So it's easy to prove this. Okay, so you see that the Fourier transform is a train of Dirac delta. I mean, train of Dirac delta is more terminology that generally is used by engineers. Okay, and this is like a way, something that I did during COVID-19. And so this is the Fourier transform of our phi. This is the transform of the derivative, and this is quite an easy result. The problem is what that I introduced before is here on gamma, okay? Because you see here on gamma, we have all this. Why? Because the same problem, like we don't have actually, we cannot go in the transform domain. So I'm sure, quite sure, no, let's go back. I'm quite sure that this result can be improved, okay? But not if we are not able to fix this problem. As an application, we can see something using the local fractional derivative, okay? So one definition of fractional derivative, a local fractional derivative, is what you see here, where n stays between 0 and 1. I know that the definition of fractional derivative has a lot of problems, so we don't want to discuss here this, okay? But some authors are using this. So if we do this, we can prove that the n derivative of f of x is given by this. This was proved by a Chinese researcher, Yang. I know that there are many Yang in China, but I know this is a very popular surname. But AP of beta is given by this. You see over there, we have our connection coefficient, where L is equal to 1, because it's N1 MQ. Okay? So this is an example. In this example, I took a very easy function, you see over there. So since the function is L2 with respect to this, you know, the second partial derivative is bounded on 0, 1, and is in L2W. Okay, so we can use. We can try to approximate it in this way, with this truncated form. And here we have two plots. You see, here we compare g of x and the approximation using Chebyshev wavelets. Here we see g of x if we impose k star and m star. So going back, no. Going back here, you see k star and m star. And here is an approximation between the fractional derivative of g of x and the approximation once more for k star equal to 9 and m star equal to 31. So some conclusion. This is what we saw in the last three points: integral equation, older spaces, and Campanato Moro spaces. This will be three applications of these wavelet families, because we already have results for the Chebyshev wavelets. These are some references. In particular, the third paper, Horadam, is the paper where you can find everything you want on Vieta-Lucas polynomials. And the last one is a characterization of the Cantor function if you want to interconnect with the definition of local fractional derivative. Thank you.